Hi everyone. I'm sorry I couldn't be there in class today. I'm out at a conference, but nonetheless, we will have our lecture today on mass percent and calculating molecular formulas. So let's get started. So if you've read chapter 6 already, you know that we have a chapter question that basically is going to guide this chapter into figuring out, how much of a particular element is in a substance. And for this one, it is how much sodium is in a given amount of sodium chloride. So this question is kind of similar to asking how many leaves are on a clover. So if we take a look at the clover leaf here on the left, we can basically say, hey, we've got one clover, and within the clover we have 1, 2, 3 leaves. Right, so there's a 3 leaf to 1 clover ratio here in this example. So what if we were to ask how many leaves are in 14 clovers? Well, we can use this ratio here of 3 leaves to 1 clover as a conversion factor to help us figure out how many leaves would be in 14 clovers. So we can see we can set it up with our 14 clovers to begin with, because that's what we're given in the question, right? And then we can use our 1 clover equals 3 leaves as a conversion factor here, making sure that clover is on the bottom of our conversion factor so that it cancels the clover we start with, and leaves is on the top so that we end with the unit that we desire, which is leaves. So once we do the math, we multiply on the top, divide by the bottom. We get 14 times 3 divided by 1 is going to give us 42 leaves. So this is kind of the same thinking that we're going to do, obviously not with clovers and leaves, but with elements and their constitutive compounds. All right, and I do apologize in advance for some of the formatting that's all weird on these slides. When I import it into this program, the PowerPoints don't come out cleanly. So if you've printed yours, you'll have it all nice and neat on your notes. All right, so let's see how this works with actual chemicals and chemical formulas. So when we're given a chemical formula, it's giving us a ratio between the elements and the molecules for that particular compound, right? So, for example, the compound CO2, carbon dioxide, indicates that there are 2 oxygen atoms and 1 carbon atom per CO2 molecule, right? So if we were to take a look at the bits and pieces here, we'd say, all right, there's 2 oxygen atoms in 1 molecule of CO2. We could also say that there is 1 carbon atom in 1 molecule, right, of CO2. Same idea with the leaves on the clover. Now, if we kind of expand that out, instead of talking about individual atoms, what if we talked about the counting unit dozen, right? So if we had 2 dozen oxygen atoms, we'd have there would be 1 dozen CO2 molecules. So another way to say that is in 1 dozen CO2 molecules, we have 2 dozen oxygen atoms, and then again, that's because we have that 2 here representing how many atoms of oxygen are in that particular compound. So the ratio is a 2-to-1 ratio, 2 moles of oxygen per every 1 mole of CO2. Let's put the CO2 in the box again since it got moved by the program. Okay, so these are going to be important conversion factors that we're going to be using while we are working through this chapter. So let's take a look at CH4, right? In 1 molecule of CH4, we can say that there is 1 mole of carbon, and in 1 mole of CH4, we could say that there are 4 moles of hydrogen, right? Just looking at our subscripts here, 4 here, and then there's none for carbon, so it's obviously a 1. Okay, same thing here for NaCl. If we had 1 mole of NaCl, there would be 1 mole of sodium atoms and 1 mole of chlorine atoms, because it's a 1-to-1 ratio. Does that make sense? Hopefully it does, and if not, please make sure you ask questions when I'm back next class. All right, so we can use these conversion factors that we were just talking about to help us in answering how many moles of a particular element there would be in a given amount of compound. So here is a question. It says, how many moles of oxygen are in 18 moles of CO2? Right? So basically what we're trying to figure out is we are given moles of CO2, and then we need to figure out how many moles of oxygen atoms there are in this compound. So here is our conversion factor. 2 moles of CO2 in 1 mole of the CO2, 2 moles of oxygen in 1 mole of the CO2 compound. Again, remember we get that because there's a 2 right after the oxygen, indicating 2 atoms of oxygen in the compound. So if we just had 1 compound of CO2, we could say 2 atoms. Here, we're going to expand it out to moles. So for every 1 mole of CO2, there are 2 moles of oxygen atoms. So sorting what we know, we're given 18 moles of CO2, and we need to find how many moles of oxygen atoms. So here is how we're going to set it up. We always start with what we're given, our 18 moles of CO2, and then we're going to use our conversion factor, and I'm sorry again that it's funky, but it should say 2 moles of oxygen over 1 mole of CO2, right? So again, that CO2s are going to cancel top and bottom, and we end up with moles of oxygen in the end. All right, and remember, the math goes multiply on top, divide by the bottom. So we have 18 times 2 divided by 1 is 36. 36 moles of oxygen in 18 moles of CO2. All right, so let's try another example. Here's another one that says determine the number of moles of oxygen in 1.7 moles of calcium carbonate, CaCO3. So remember, given this information, right, we can look at our subscripts and say, okay, for oxygen, there are 3 moles, M-O-L, 3 moles of oxygen in 1 mole of the entire compound CaCO3. So this is going to be our conversion factor for when we set this up. So remember, we always start with what we're given in the question. So we're going to start out with 1.7 moles of CaCO3. And we're going to use our conversion factor, making sure that moles of CaCO3 are on the bottom so that it cancels our moles of CaCO3 that we start with. And moles of oxygen are on top because that's what we want to end with. All right, and so remember, these units and numbers stick together. So wherever we see moles of CO3, we're going to put the 1. And wherever we see the unit moles of oxygen, we're going to put the 3. So the 3 is going to go on top. The 1's going to go on the bottom. And we are going to multiply the top and divide by the bottom. So 1.7 times 3 divided by 1 is 5.1 moles of oxygen. So if we had 1.7 moles of calcium carbonate, it would equate to 5.1 moles of oxygen atoms. All right, so we're going to take what we just learned and then expand it just a little bit. Because remember, in real life, we're not really working with moles, we're working with grams of certain substances. So we're going to just use the molar mass now in order to go from moles to grams. So if we were trying to answer the question, what is the mass of sodium in 15 grams of sodium chloride? Okay. Remember, mass is in grams, so we can't go directly from grams of sodium chloride to grams of sodium. We cannot do that directly because remember, the periodic table gives us the molar mass. Okay, so it gives us how many grams are in a mole. So we can't just go grams of one guy to grams of another. And I know we talked about it and you guys learned about that concept in regular chemistry in our stoichiometry unit. So that's why we had to always go from grams to moles and then moles to grams. So if you remember mole island conversions, moles was always in the middle because moles is our middleman. Whatever we start with, we have to go through moles in order to end up with a certain number of grams of a different substance in the end. So what we're going to do here instead is we are going to start with what we're given. That's our 15 grams of NaCl. And then, because we can't go directly from grams of NaCl to grams of sodium, we're going to turn it to moles of NaCl first. And we can use our periodic table to do that. Once we are in moles of NaCl, then we can use our conversion factor that we just learned about with figuring out, how many moles of a element are in a particular number of moles of a compound. So we're going to use our conversion factor here to go from moles of sodium chloride to moles of sodium. And in this particular substance, if we have 1 mole of sodium chloride, because it's a 1-to-1, 1 atom of sodium and 1 atom of chlorine, we're just going to have the ratio 1-to-1. In 1 mole of NaCl, there's 1 mole of sodium atoms. So that's going to be our conversion factor for getting from step 2 to step 3. Okay. And then finally, when we are in moles of Na, we can again use our periodic table to turn it back to grams of sodium. Okay, so we're going to set up 3 bridges for these. And it's actually going to look just like this here. So we start with what we're given, our 15 grams of NaCl, and we're going to use our periodic table to turn it to moles of NaCl. So remember, our periodic table gives us the number of grams in 1 mole of that substance. So 1 mole of NaCl is 58.44 grams. And remember, we just got that from adding up 1 Na and 1 Cl atom from the periodic table. You end up with 58.44. Our next step, we said, was going to go from moles of NaCl to moles of Na, just sodium by itself. And remember, to do that, we were going to use our conversion factor. In 1 mole of NaCl, we have 1 mole of sodium atoms. So we have a 1-to-1 ratio there. And then last but not least, we're going to go from moles of Na to grams of Na, again using our periodic table. By looking up sodium on the periodic table, we can see that it's 22.99 grams per mole. So we're going to put 22.99 on top with Na and 1 on the bottom for moles of Na. So when we multiply everything on the bottom, and then we multiply everything on the top first, and then we multiply everything on the bottom and divide those two, we're going to end up with our answer here. Okay, with the correct amount of sig figs. Remember, sig figs always comes from how many sig figs you start with. Remember all the conversion factors in between Don't count for sig figs because they are consistent, like constant numbers. So for this, we're going to see in 15 grams of sodium chloride, it equates to 5.9 grams of sodium. All right, so we've seen in the previous couple of examples that, remember, we cannot go from grams to grams directly. So from grams of one substance to grams of another, we cannot go between them directly. We have to go to moles first. So the chemical formula gives us a relationship between moles of substances and not between grams. So here is a general schematic of all the of how we're going to solve all the different kinds of problems here in this chapter. So we'll start with the mass of our compound. The first thing we'll do is turn it to moles of the compound. Then we'll use our chemical formulas in order to get a conversion factor to turn it to moles of the element. And then finally, we can use our periodic table again to go from moles of the element to mass or grams of the element. So let's use this knowledge in order to answer this unit question here. It says the FDA recommends that a person eat less than 2.4 grams of sodium per day. What is the most amount of NaCl, sodium chloride, or table salt, that can be consumed? And we're going to figure this out in grams. So first thing that we want to do is remember that we cannot go from 2.4 grams of sodium directly to grams of sodium chloride, right? That is a big no-no. We can't do it in one step. So the first thing that we're going to have to do is go from grams of sodium to moles of sodium. Once we have moles of sodium, we can go to moles of sodium chloride. And then from moles of sodium chloride, we can use our periodic table again to go to grams of sodium chloride. All right, so that's kind of our setup that we're going to do. So let's start. We're going to start with what we're given, 2.4 grams of Na. And then our first step is to go to moles of Na. And so grams is going on the bottom so that it cancels. And if we take a look at the periodic table, we can see that in 1 mole of Na, there is 22.99 grams. Okay, so that's our first step, getting rid of grams of Na and turning it to moles of Na. Our second step is going to use our ratio to go from moles of Na to moles of sodium chloride, NaCl, right? And if we are taking a look at the compound for NaCl, we can see that there's 1 sodium atom and 1 chlorine atom in the compound. So if we have 1 mole of sodium chloride, we're going to have 1 mole of sodium atoms. So here we're going to have a 1-to-1 ratio. 1 mole of sodium atoms are in 1 mole of sodium chloride. All right, so again, that takes care of our moles of sodium units. And now the last step is to go from moles of sodium chloride, so that'll go on the bottom so that it cancels, to grams of sodium chloride. Again, we're going to use our periodic table for this, and we'll see that in 1 mole of sodium chloride, if we add a sodium and a chlorine together, we're going to get 58.44 grams. So this conversion is going to cancel our mole of NaCl unit, and we're going to end up with our answer after we multiply everything on the top and then divide by everything on the bottom. We're going to get 6.1 grams of NaCl. Okay. So the FDA recommends a person eat less than 2.4 grams of sodium. So in order to kind of abide by that, you should have no more than 6.1 grams of sodium chloride. And if you want to know what that looks like, after the lecture, you can come on up. I have a little tray of exactly 6.1 grams of salt. And so you can see it's actually not that much. If you think about how much salt you put in, you sprinkle on, everything that you eat or you cook with, or if you eat a lot of processed and preserved foods, there is quite a bit of salt in there as well. So always be careful with how much salt you've got. All right, so that was one way that we can express how much of an element is a given compound using that, molar ratio within the compound. Here is another way to express how much of an element is in a compound, and we call this mass percent or mass percent composition. So this is basically the element's percentage within the total compound that it is in. So in order to kind of solve for the mass percent, what we're going to do is we're going to take the mass of the element X in the compound, and then we're going to divide it by the total mass of the entire compound. Okay, so it's all percentages are parts out of wholes, right? So if we have again, we're talking about sodium in sodium chloride. We're going to take the mass of sodium and then divide it by the total mass of sodium chloride that we have. So here's an example. We've got an example here that says, suppose 0.358 grams of chromium react with oxygen to form 0.0523 grams of metal oxide. What is the mass percent of chromium? Well, we know we've got 0.358 grams of chromium here, and we've got 0.53 grams of the chromium oxide. So what we'll do, is we will take the mass of the chromium and put it on top, and we'll take the total mass of the metal oxide, or in this case, the chromium oxide, and we'll put it on the bottom. When we divide the two, we get a percentage of 68.5%. So what that means is that in that metal oxide, that chromium oxide powder, 68.5% of that mass is due to the chromium atoms in that compound. All right, so it seems easy enough to do the mass percent. Just take the mass of the single element and divide it by the total mass of the compound that it's in. So guess what? If we have a percentage, we can use that as a conversion factor. Yes, more conversion factors. Remember, I mentioned the very beginning of the semester, there's only two types of math problems that you're going to do in here. Either one, it's going to be conversion factors, where we are going to be canceling units, right, to go from one unit to another. Or number two, it's going to be plugging numbers into a specified equation, like the Q equals M times C times delta T equation. That's the only two types of problems we do in here. We either plug and chug or we do conversions. So we're going to see that we can come up with a lot of different conversion factors given the information in a particular problem. Okay, so here we can use the mass percent as a conversion factor between the element and the grams of a compound. So for example, if we know the mass percent of sodium in sodium chloride is 39%, what that means is if we think about it in terms of 100, right? Because typically in percentages, we think of, something out of 100 of it. So 39% would be 39 grams of sodium, okay, in every 100 grams of sodium chloride. Okay, so we took that percent and we turned it into a conversion factor. So we can use the conversion factor either this way, where we have the grams of sodium on top and the grams of NaCl on the bottom, or if we need to convert to grams of sodium chloride, we can flip it and we can have the sodium chloride on the top and the grams of sodium on the bottom. So let's see how this works. Here's an example question. It says, if a woman consumes 22 grams of sodium chloride, how much sodium does she consume? And remember, here's our conversion factor. We know that sodium chloride is 39% sodium by mass. So that means for every 100 grams of sodium chloride, 39 grams of it is the sodium itself. So that's our conversion factor. So we start with what we're given in the question, our 22 grams of sodium chloride, and then we use our 39 over 100 as our conversion factor. And when we cancel our units, multiply on top, divide by the bottom, we get our answer, 8.6 grams of sodium chloride. Remember, we have to do the correct number of sig figs. We got to match it up to what we start with. So we started with 2 sig figs, and so our answer should be rounded to 2 sig figs as well. So that's how it works with mass percent and using it as a conversion factor. Another trick of the trade that we can do with mass percent is calculating the mass percent of any element in a compound from the chemical formula for that compound. So it's kind of like tying in what we did at the very beginning of this lecture with looking at, how many moles of a certain element are in a mole of a compound with that element in it. And then also combining it with the mass percent. So it's kind of like conjoining those two together. So what we'll do here is we will, to get the mass percent of an element X in a compound, we're going to take the mass of element X in 1 mole of that compound and then divide it by the mass of 1 mole of the compound itself. So for example, here's a question that says, what is the mass percent of chlorine in the chlorofluorocarbon CCl2F2? So it should be written like this, CCl2. So there's 2 atoms of chlorine, 2 atoms of fluorine, and 1 atom of carbon in this compound. So it's asking for the mass percent of chlorine. So to do that, what we're going to do is we're going to use the molar mass of chlorine on the periodic table, which is 35.45. And from the compound itself, we can see that there's 2 atoms of chlorine, so that's why we've got a 2 in front here. So we have 2 times the molar mass of chlorine, which is 35.45. All right, that's going to be the top here with our mass of element X in 1 mole of compound. And then we are going to be dividing it by the molar mass of the whole compound together, the whole chlorofluorocarbon. So we're going to add up 1 C, 2 Cl's, and 2 F's all together from the periodic table. And when we do that, we get this total mass of 120.91 grams. So here we've got our mass of just the chlorine atoms in this compound, and then we're going to divide it by the mass of the whole compound itself. And when we do that, we get an answer of 58.64%. So if we have a mole of this chlorofluorocarbon, CCl2F2, 58.64% of its mass is from the chlorine atoms alone. That's kind of what it means. So let's take a look at an example of calculating mass percent of a single element in a compound. So this one says calculate the mass percent of chlorine in Freon 114. And it gives us the chemical formula right here. So C2Cl4F2. So what we're going to do is we need to focus on chlorine. So there's 4 atoms of chlorine in this molecule. So we're going to do 4 times the molar mass of chlorine, which is 35.45. And then we're also going to take the whole mass of the entire molecule. So add up all of those atoms together. And we're going to put that on the bottom. So that's 203.82. And 35.45 times 4 is 141.8. So this is grams of Cl over 203.82 grams of our Freon 14, C2Cl4F2. And when we do the math, we end up with 69.58% chlorine in this compound. So what's the mass percent of chlorine in Freon 114? It is 69.5%. There you go. All right, so moving right along, the last part of this lecture, we're going to be focusing on using the skills that we learned in the last couple of slides in order to help us figure out the empirical formula for compounds and the molecular formula for compounds. So let's just kind of go over the difference between the two. So when labs analyze different compounds, they aren't often given the chemical formulas directly. So you'll put a substance in the machine and it will tell you, kind of how many grams of a particular, or percent actually, it'll tell you the percentage of a particular atom in the compound, but it won't tell you exactly what the molecular or chemical formula is. So it gives you the relative masses of each element present in the compound. And so, but, we can determine what's called the empirical formula, or the smallest whole number ratio of each type of atom in that compound. So it won't be the specific number of each atom. That's what we call molecular formula. So this empirical formula is the smallest ratio of each type of atom, and the molecular formula is the exact number of atoms. So let's give an example here. We've got hydrogen peroxide. Hydrogen peroxide's formula, molecular formula, exact, which tells you the exact number of atoms in the element, is H2O2, right? Hydrogen peroxide, each molecule has 2 hydrogens and 2 oxygens in it. Now, if we were to use the smallest whole number ratio, those 2's would cancel out and we'd end up with the ratio HO, one of each, one H and one O, right? So that's the big difference between empirical formula, which is the smallest whole number ratio, and molecular formula, which tells you the exact number of elements in the molecule. Okay, so under laboratory analyses, we can typically figure out the molecular formula, smallest whole number ratio, and we'd have to do a little bit more work to figure out the molecular formula. So let's see how this works. All right, so here's an example question. It says, suppose we decompose a sample of water and find that it produces 3 grams of hydrogen and 24 grams of oxygen. What is the empirical formula? All right, so remember, the empirical formula represents the ratio of atoms or moles, but does not represent the ratio of masses, right? So So remember, if we are given grams, we have to convert to moles first. That's the bottom line. That's what it means. Molecular formula is going to tell us the mole ratio, but not the mass ratio. So if we are given 3 grams of hydrogen, if we know that, then the first thing we have to do is convert it to moles of hydrogen. So again, we'll use our periodic table. In 1 mole of hydrogen, there's 1.01 grams of hydrogen. So we will do the math, and we'll end up with 3.0 moles of hydrogen. Same thing we'll do with oxygen. We're going to turn our grams of oxygen into moles of oxygen. So in the laboratory analyses, we said we are given 24 grams of oxygen. Again, we'll use our periodic table. 1 mole of oxygen is equal to 16 grams of oxygen. So when we divide, we're going to end up with 1.5 moles of oxygen. Okay. So now that we're in moles, right, we can kind of start making our first very crude empirical formula, right? So because it says moles, we could say, H3O 1.5. All right, but if you've ever looked at formulas, chemical formulas of any kind, you know that we never use fractions. Okay, it's always whole numbers. So once we have, if we don't have whole numbers from converting to moles, from grams to moles, then what we'll do is we will divide both of them by the lowest number. So here, though, it's 1.5. So we'll divide both sides by 1.5. And when we do that, 3 divided by 1.5, right, is 2. So now we've reduced 2 down to H2. And then 1.5 divided by 1.5 is 1. So we have 1 oxygen, so H2O. So that's how that works. So again, first step is to go from grams to moles. Second step is to put that into a beginning chemical formula. Third step is to divide those subscripts. Okay, if they're not whole numbers, divide by the lowest of them. So in this case, it was 1.5. And then fourth step, just reduce that down to our lowest whole number ratio, H2O. All right, let's take a look at another example, because this is probably the most complicated part of this chapter and the most confusing. So let's go through another example, and then you guys will have some time to practice with some Socrative questions as well. So the more you get it under your belt, the easier it is. So I also suggest going home and making sure that you can do those practice problems within the chapter as well. Do as many as you can. All right, so here's another one. It says you decompose a compound containing nitrogen and oxygen in the lab and produce 24.5 grams of nitrogen and 70 grams of oxygen. Calculate the empirical formula of the compound. So the first thing we're going to do, remember, is we have to convert grams to moles. So the grams that we're given mean nothing right now. We need to convert it to moles first. So we'll take our 24.5 grams of nitrogen, convert it to moles using our periodic table, PT. When we do that, we end up with 1.75 moles of nitrogen. We'll do the same thing with our 70 grams of oxygen that we are given from the computer analysis. And we're going to turn that into moles. It's from grams to moles of oxygen. Again, using our periodic table, 1 mole of oxygen is equal to 16 grams of oxygen. And so when we do the math, we end up with 4.38 moles. So remember, that's our first step, going from grams to moles. Our second step all right, is putting that into a crude formula. So it's kind of funky here. So let me write it I'll write it right here. So our crude one is N 1.75, because that's how many moles we figured out there was. And then O 4.38, right? But remember, formulas are always whole numbers. So then we do our third step, which is divide by the lowest number. So we'll divide both sides by 1.75, divided by 1.75. And if we do this, we end up with N102.5, which still doesn't help us because it's still not a whole number, but it's a much easier whole number. It's a much easier number to get to a whole number, right? Because all we need to do is to get 2.5 to a whole number, let's multiply them by 2. So if we multiply oxygen by 2, that means we have to multiply nitrogen by 2, multiply the whole compound by 2. And when we do that, we end up with N2O5, right? So this is our actual compound, N2O5. So that's kind of our fourth step there. So again, convert the grams that you're given in the lab analyses to moles first. Then use those moles as little subscripts for the first rendition of our compound. And then we're going to divide by the lowest number there for our subscript. In this case, it was 1.75. Right? If it ends up being a whole number for both of them, great, you're done. You've got your whole number ratio for the compound. But if, like this one, it does not end up as a whole number, then we need to figure out a multiple to multiply it by to make it a whole number. So in this case, it was multiplying both N and O by 2 to give us the whole numbers N2O5. All right, so we just need to remember we need whole numbers in our formula. All right, let's do one more, because again, this is hard, this is weird. We didn't do this in regular chemistry. So we're going to do lots of problems with these. Here is a different kind of way to set it up, or the way that it's going to be given to you. But it's the same setup, the same 3 or 4 steps that we just did. In this case, it says a laboratory analysis of aspirin determines the following mass percent compositions. So instead of giving us grams, we're given percent. So we know in this compound, 60% of the mass is carbon, 4.48% of the mass is hydrogen, and 35.53% of the mass belongs to oxygen. And it just says, find the empirical formula. Great. Awesome. All right. So the first thing that we're going to do in this case is we are going to turn the percents, into moles. So basically what we're going to do is we're going to think of this as being part of a 100-gram sample, right? So if it's a 100-gram sample and 60% of it is carbon, that means we have 60.00 grams of carbon in this particular substance, okay? Same thing here. If we have a 100-gram sample of aspirin and 4.48% of it is hydrogen, that means 4.48 grams is hydrogen. All right, and then last but not least, 35.53% means that it's 35.53 grams of oxygen. So see, from the percents, we just convert it to grams. Okay, so we basically don't even convert. We just change the percent sign into a grams sign for each of those elements. All right, now that we are in grams, first thing we need to do, remember, is turn them to moles. So we're going to take each and we're going to turn it to moles. So 60.00 grams of carbon. In 1 mole of carbon, we have 12.01 grams of carbon. So 60 divided by 12, it's going to give us 0.4999 moles of carbon. Okay. If we do the same thing with hydrogen, 4.48 grams of hydrogen. We're going to turn that to moles. So 1 mole of hydrogen is equal to 1.01 grams of hydrogen. And so if we do that math, we get 4.44 basically moles of hydrogen. Okay. And then last but not least, we do the same thing with oxygen. We're going to turn our 35.53 grams of oxygen into moles of oxygen. So in 1 mole of oxygen, there's 16.00 grams of oxygen. So when we do that math, we end up with 2.22 moles of oxygen. Okay, so we turned our percents to grams, our grams to moles. Now the next step is to put together our initial chemical formula. So C 4.99, H 4.44, O 2.22. Okay, super ugly because it's not whole numbers. Okay, so that comes to our next step. Let's divide all of them by the lowest number, in this case 2.22. So we're going to divide all of them by 2.22. And we're going to end up with C 2.25, H 2.01, right? Okay, still not there because we still don't have purely whole numbers. So the last step then would be to figure out, okay, what could we multiply 2.25 by in order to get a whole number, to get it up to a whole number? Well, here we've got 2 1/4. So we know 4 quarters makes a whole dollar. So let's multiply all of them by 4. So we're going to do 2.25 by 4, 2 times 4, and 1 times 4. And so when we do that, we're going to end up with our final answer because they'll all be in whole numbers. So 2.25 times 4 is C9. 2 times 4 is 8, so that's H8. And then 4 times 1 is 4. So there we go. C9H8O4. That is our empirical formula for aspirin. All right, so again, lots of ugly steps. Please make sure that you go back and do lots of practice problems in the textbook for this, because the more you do it, the easier it'll come. But last but not least, let's review the steps. We turn our, actually, go back there. The first step is turning our percents to grams. Then we're going to turn our grams to moles. So this whole step over here was step 2, right? Turning them to moles. And then our third step is to make our crude or initial chemical formula. Then our fourth step is to divide by the lowest number. Then our fifth step is to multiply, right, by a multiple to get whatever is not in a whole number up to a whole number. And then very last but not least, we write out our actual formula from that, C9H8O4. H8O4. Okay, so as not to complicate things even further, if we are given the molar mass of a particular compound, we can actually use the molar mass in order to calculate the molecular formula. Meaning, remember, molecular formula is the exact amount of atoms in the compound, not just the smallest whole number ratio, but the exact amount of atoms in a compound. We can figure that out as long as we know the molar mass of the substance as well. Okay, so here we can determine the molecular formula from the empirical formula as long as we have the molar mass of the compound. So just remember the molecular formula is always a whole number multiple of the empirical formula. So molecular formula is going to be the empirical formula times some factor of n. And that's, if we know the factor of n and we know the empirical formula, we can do the math to figure out the the molecular formula. Okay. So here is a example here. It says find the molecular formula for fructose from its empirical formula CH2O and its molar mass 180.2 grams per mole. Okay. So if we take our formula here, molecular formula equals empirical formula multiplied by the factor n. In order to figure out that factor n, basically what we're going to do is we're going to take the molar mass and we're going to divide it by the empirical formula. The empirical formula is molar mass, I should say. So here we're given the molar mass of fructose, which is 180.2, so we're going to put that on top. And then when we add up CH2O altogether on the periodic table, that ends up being 30.03 grams per mole. So 180.2 divided by 30.03 gives us a factor of 6. So that means what we're going to do is we're going to multiply CH2O by 6, each of those little subscripts by 6 in order to get the molecular formula for this. So the molecular formula, if we multiply everything by 6, would be C6, all right, H2 turns into 2 times 6 is 12, and then oxygen, 1 times 6 is 6. So C6H12O6 is the molecular formula for fructose, knowing our empirical formula and molar mass. So because this is a one step further complication from empirical formula, we're going to do another example. So here is an example. It says naphthalene. Remember we talked about naphthalene when we talked in the very first lecture about distillation and the crude oil distillation tubes or apparatuses that we see sometimes going off the freeway, especially towards LA. Naphthalene was one of the layers of crude oil that when it gets up to a certain temperature, naphthalene will evaporate and they can trap that and use it for different household chemicals. And in this case, we're going to be using this in mothballs. All right, so it says naphthalene is a compound containing carbon and hydrogen that is used in mothballs. Its empirical formula is C5H4, and its molar mass is 128.16 grams per mole. What is the molecular formula? So what is the actual formula for naphthalene? So let's start by figuring out, remember, N is we're going to figure this out by putting the molar mass over the mass of the empirical formula. Right, so we're going to do C5H4 mass, and then we're going to put that on the bottom. So here, our molar mass that we're given is 128.16 grams per mole. And then when we add up C5H4, we get 64.09 grams per mole. So remember, that's from adding up 5 carbons and 4 hydrogens together. We get 64.09. And then when we divide those two numbers, we get 2. Okay, so our N factor is 2. So what we're going to be doing is we are going to take our C5H4 and we're going to multiply each of these subscripts by 2. So 5 times 2 is 10, 4 times 2 is 8. So naphthene's molecular formula is C10H8. And that's how that works. So this is the last slide, the last thing in this lecture. So we've learned about using the chemical formula and like the atoms in it over the actual chemical formula as a conversion factor. Okay. We also talked about mass percent of chemical formulas, and then we kind of mashed that together to do problems where we were doing empirical formula, and now if we have empirical formula and molar mass, we could figure out the molecular formula. So once again, it's a lot of new concepts that we did not touch too much base on in regular chemistry. So you want to make sure that you do the Socrative coming up, and then also take a look at all of the example problems within the chapter 6 to make sure you understand how this works. And as always, if you have any questions, please come see me next class. I'll be back next class. You can come see me, and I can answer any questions that you have.